So today we're going to talk about graphs. So what's a graph? Well, a graph is a set of edges and vertices, and the rule is every edge begins and ends at a vertex. So what I say is there are no dangling edges. Every edge has to begin at a vertex and end at a vertex. So here is an example of a graph. I call capital V my set of vertices, V1 through V5. Capital E my set of edges, which in this case, E1 through E4. Okay, so that's what a graph is. It's just a set of edges and vertices. Now, what's a subgraph? Well, a subgraph is any piece, any subset of my original graph that's also a graph. So if I look at this as my graph, one possible subgraph is this one little piece. So that's a subgraph. Now, if I were to leave out this vertex right here, notice it's left out here, then that's not a subgraph. Why? Because this edge is dangling. Right? It's got to end at a vertex, but there's no vertex there. Okay, so what's a path? Well, a path is any little path that I can walk on my graph. So if I look up here at my original graph, if I go from V1 to E1 to V2 to E3 to V3, so that's V1 to E1 to V2 to E3, ending at V3, so this path right there, that's a path. Notice it's an alternating sequence, so it starts and ends at a vertex, and there's edges in between. Another path might be V1 to E1 to V2 to E1 to V1. So V1 to E1, that puts me at V2. If I walk along E1 again, and I'm back at V1, there's a path. So that path goes from here to here, back. That's what a path is. The length of a path is the number of times an edge is listed. So every time I walk over an edge, I add 1 to the length. So if I look at this path right here, which I've rewritten down here, I notice that I walk over the edge E1 and the edge E3. So that's a path of length 2 because I've walked over 2 edges. If I look at this path going from V4 to E4 back to V4, let's look and see what that looks like. V4 to E4 back to V4. That's a path of length 1 because I've only walked over 1 edge. Now, if I look at this path, which I've copied down there, and I start at V1, I walk over E1, I go to V2, I walk over E1 again. Well, every time I walk over an edge, every time it's listed in my path, it adds 1 to the length. So that's of length 2. And finally, if I just do the vertex V2, that is, I stick at the vertex V2 and I don't move anywhere. V2 is this vertex right there, but I never move. Then that, of course, is of length 0. So that's what a path is, and that's what its length is. And now I want to talk about what a digraph is. Well, a digraph is a graph in which edges have direction. So not only do I have an edge, but some edges are only one way. I can only walk one way. Here's an example. If I look at the edge E1, I have this little arrow here that says I can only walk from V1 to V2. I cannot walk from V2 to V1. And that's what a digraph is. Digraph is short for directed graphs. So the point is, the arrows indicate the direction. So we started a whole new type of structure, graphs, and so we're going to have lots of definitions. The next definition is the word incidence. And incidence is the graph connection between edges and vertices. We say an edge is incident on a vertex, or a vertex is incident on an edge. So if I look at this graph right here, I notice that V1 is incident on E1. That means E1 ends at V1. They touch. So that's the concept of incident. All right, so V1 is incident on E1. By the same token, I can say E2 is incident on V3. Why? Because E2 is connected to V3. So we can say a vertex is incident on an edge, or we can say an edge is incident on a vertex. The next definition is what it means to be adjacent. We say two vertices are adjacent if they're incident on the same edge. So what does that mean? That means two vertices are adjacent if there's an edge between them. So if I look at V1 and V2, there's one edge that connects them. That makes V1 adjacent to V2. You might also see that what? V3 is adjacent to V2. So I should change that. V3 is not adjacent to V2, or is not adjacent to V1, but it is adjacent to V2. So let's change that. All right, so V1 is adjacent to V2, and V3 is adjacent to V2. And like I said before, though, V3 is not adjacent to V1. Why? Because there's not one edge between them. Okay, now let's talk about parallel edges. Well, parallel edges are incident on the same two distinct vertices. All right, so if I look at this graph right here, I notice what? E3 and E2, they both are incident on V2 and incident on V3. That's what they mean by parallel, right? So if you kind of look, that edge is parallel to that edge. What do we mean by a loop? Well, a loop is an edge incident on only one vertex. If I look at this graph right here, I see what? E4 is a loop. Get it? If it's incident on only one vertex, and it's got to begin at a vertex and end at a vertex, then a loop is an edge that begins and ends at the same spot. Looks like a loop. what do I mean by an isolated vertex? An isolated vertex is incident on no edge. Now, so incident on no edge means there is no edge that touches it. So if I look at this graph right here, it's easy to see that V5 is what I call an isolated vertex. And now I'm going to define what I mean to be a simple graph. A simple graph is simply a graph that has no parallel edges or no loops. Okay, so if you want an example of a simple graph, here it is. If you look at that, by the way, this vertex V3 is meant to be connected right there. This is a simple graph. Why? Because there are no parallel edges or loops. This graph over here, on the other hand, is not a simple graph. Why? Because, like I said before, E3 and E2 are parallel edges. So if it's got a loop or if it has a parallel edge, then it is not a simple graph. A graph is connected in case I can find a path between any two vertices, any two distinct vertices. That essentially means I can walk from one vertex to any other vertex by going along edges that are in my graph. So if I look at this graph right here, it's easy to see it's connected. Why? Because I can walk from any vertex to any other vertex. I could go from V1 to V3 that way, or I could go from V3 to V2 that way. The point is, I could start at any vertex and get to any other vertex. That's what it means to be connected. If it's not connected, then obviously that means I cannot walk from some vertex to some other vertex. And so if you want an example of that, there is a graph that's not connected. Why? Because I cannot walk from V5 to V4 along any edge. And finally, the components of a graph, or the component of a graph containing a vertex V, is the largest connected subgraph containing V. All right, so suppose I take the vertex V1 and I want the component containing V1. What is it? Well, I start with V1 and I walk in all directions that I possibly can. And when I've walked everywhere I can walk, that piece is called the component containing vertex V1. By the way, it's also the component containing vertex V3. And then if I look at this piece here, that's another component. That's the component containing V4. And this is the component containing V5. So the point is, if I look at this entire graph as one graph, it's easy to see I have 1, 2, 3 components. By the way, that brings in mind a theorem that says if a graph is connected, it only has one component. In fact, a graph is connected if and only if it has simply one component. Well, I think I'm going to stop here, and that's got some of the basic definitions with respect to graph theory.